Hi, folks. Thank you so much for coming to this year's union session. This is the first year that we've tried this, so it is a bit of an experiment. And this is U13B, Student Engagement to Enhance Development. Everyone in the room is a OSP award winner from 2016. And we're going to be going through these really quickly. So just really briefly, my name's Kelly Klima. I am a former OSPA winner. And this is Leslie.
I work for AGU. I'm a student programs coordinator, and Kelly was kind enough to ask me to be the co-convener for this session.
So as you guys know, each year AGU and sections and focus groups, they recognize roughly the top 3 to 5% of folks through this Outstanding Student Paper Award. And this year, for the lightning sessions here, as well as the e-lightning sessions we'll have tomorrow, we're having all of the winners who are able to make it come and give a brief talk. Now, for you winners, I know you've been said this on email, but just to double check, you got 2.5 minutes. We're going to hold to that as closely as possible. We should have a green light for the first minute, a yellow light for the second minute, and a red light for the last 30 seconds. And I will hit you over the head with a hammer if you take longer than that. No, just kidding. No hammer. But let's try and keep things on time because there's a lot of folks and not a lot of time. Sound okay? All right. Yeah. Good. Okay, so I think our first person is actually Alexis Shusterman, who's talking about 5 years of Beacon with a 2 in it. So you'll have to tell me how to say that. First, results and lessons learned. So please come on up. One thing, sorry to interrupt. Please hold your questions and hold your applause till the end because we only have 30 seconds in between each person. So. But I love the initial round of applause. This is great.
All right. Hi, y'all. So it has been estimated that more than 70% of anthropogenic CO2 emissions originate in cities, and this fraction continues to grow. In urban areas, we see a huge number of disparate, independently regulated carbon sources that lie in close proximity. However, conventional approaches to urban carbon monitoring have typically involved a small handful of expensive instruments that, while providing highly accurate integrated signals over a given area, cannot hope to resolve the heterogeneous landscape of individual contributions to an urban total. So in order to regulate CO2 most effectively, lawmakers require much more specific information about which of their policies are working and which resources should be reallocated. So along with my advisor, Ron Cohen, we have devised a novel CO2 sensing approach that seeks to address this mismatch in scale between science and policy. Beacon, or, let's see, any next slide? There we go. Beacon, or the Berkeley Atmospheric CO2 Observation Network, is a web of more than 50 CO2 sensors stationed roughly every 2 kilometers across the San Francisco Bay Area. And each beacon sensor is therefore much more sensitive to its unique local environment, allowing us to drill down into that integrated urban total and further differentiate between CO2 that comes from cars, trucks, ships, buildings, etc. In order to afford this high volume of sensors, we rely on low-cost, off-the-shelf technologies. And although these sensors were once largely believed to provide only moderate quality measurements, we have developed in-situ corrections for meteorology and the impact of temporal drift. And using these corrections, we have demonstrated an average precision of 1.4 parts per million, which on the scales of typical urban CO2 fluctuations is virtually indistinguishable from reference instruments. So over our first 5 years of operation, we have learned a lot of strategies for minimizing noise and maximizing sensor uptime, and also implementing real-time communication of our data to a publicly accessible web portal. We have demonstrated sensitivity to atmospheric signals of all sizes, from the seasonal cycle of CO2 emission and uptake to the weekly cycles in highway traffic flow. And we've also recently supplemented our CO2 instruments with sensors for toxic gases and particulate matter that will allow us to distinguish between different co-located carbon sources. So for example, heavy-duty diesel trucks versus gasoline-powered passenger vehicles. And in the future, we are looking forward to informing more efficient policy at home while also providing a validated framework for low-cost CO2 monitoring abroad, where emissions are often on the rise, but resources are often scarce. And global warming may be a global problem, but Beacon can help us solve it more effectively, one neighborhood at a time. Thank you.
Well done, on time. And we're going to go ahead and reset the timer for our next speaker, who is Allison Hoyt, Subsidence in Tropical Peatlands, Estimating Carbon Dioxide Fluxes from Peatlands in Southeast Asia.
Hi, I'm Alison Hoyt, and today I'll talk about subsidence in tropical peatlands. So across coastal Southeast Asia, drainage and deforestation are widespread. So on the right there, you can see a typical drainage canal in an oil palm plantation, and this drainage has led to widespread subsidence across the region. So that subsidence poll shows more than 2 meters of subsidence from 1979 to 2007. And in natural peatlands, carbon accumulates under anoxic conditions, but when you add a drainage canal, suddenly oxygen can come in, and this leads to rapid decomposition. So carbon that was accumulating over thousands of years suddenly can decompose within decades. And as a result of this carbon loss, the ground subsides and releases CO2 to the atmosphere. These areas are also at risk of flooding because they're in coastal areas that are usually at or only very slightly above sea level. So how can we measure the extent of this problem? Well, traditionally, subsidence has been measured with subsidence poles. These are limited in their spatial extent, and it's also hard to reach inaccessible areas. So for the first time ever, we're using a remote sensing approach that allows us to make millions of subsidence measurements on all sorts of different land use types. So we're using INSAR, which is Interferometric Synthetic Aperture Radar, and this allows us to track changes in the ground surface elevation over time. So here's a typical time series, and every point represents a repeat pass of the satellite, and you can see that from 2007 to 2010, the ground surface subsided by almost 20 centimeters. And we're only able to track the relative differences in elevation, not the absolute elevation. We can use these time series to make maps of subsidence and see how they depend on land use, like this one. So you can see every pixel represents a subsidence time series, and in peatlands, the subsidence rates are between 2 and 5 centimeters per year. And finally, we can use the amount of peat loss and the carbon content of the peat to calculate what the total CO2 emissions from peatland degradation in Southeast Asia is, and we find it's nearly 5% of global fossil fuel emissions. Thank you.
Thanks, Allison. While we're switching out for the other one, I believe we have Karalee Brugman looking at taking Yellowstone's temperature, a new, oh boy, and this one's gonna still kill me, I practice, clinopyroxene geothermometer to improve timescales of pre-eruptive events. That was my best shot. And again, the timer here is gonna be on 2 minutes, and then it'll count up afterwards, and you have 2 minutes and 30 seconds.
Okay, thank you. I'm here to tell you why it's so important to take Yellowstone's temperature. Here we have a map of all of the lava flows in place at Yellowstone since the last caldera-forming eruption. I'm interested in the Scop Lake lava flow, shown here in blue, because it's the first eruption to occur after over 200,000 years of inactivity. For Yellowstone or any volcano to erupt after so long, first we have to remelt the magma chamber. To do this, we can add heat or new material, and once enough magma has been remelted and enough pressure builds, the volcano can erupt. During this process, minerals left over from previous eruptions can grow new shells, sort of how a tree grows rings, and each of these shells records a change in the magma chamber's history. Once these minerals erupt, we can use the information they've recorded to reconstruct this history. The mineral historian I'm using to take Yellowstone's temperature is called clinopyroxene. Each of these clinopyroxenes can have multiple shells, but we're only interested in the outermost one because this represents the last event recorded by the mineral before it erupted. Now, each of these shells has a different chemical composition, so atoms want to diffuse across that shell boundary until the mineral becomes more homogeneous. Atoms will continue to diffuse from the time the shell is first formed to when the mineral is erupted. However, the rate of diffusion is strongly controlled by temperature. So if we want to get good timescales from these minerals, first we need to get a good temperature measurement. We do that using a geothermometer. So geothermometers use the composition of a mineral and sometimes the lava it's found in to calculate the temperature of the mineral. But the problem, as you can see here, is that existing geothermometers are calibrated using a composition of clinopyroxene that doesn't overlap the clinopyroxene that we want to measure. To solve this problem, we gathered experimental data and did some of our own experiments to create a data set we used to recalibrate an existing clinopyroxene liquid geothermometer. This updated thermometer gives us a clinopyroxene temperature of 780 degrees Celsius. Using the diffusion rate, we can transfer that temperature into a time, in this case 1,200 years, between magma remelting and eruption. But what if we had used that original thermometer before we had updated it? In that case, we would get a temperature of 830 degrees Celsius, or only 350 years. That's an 850-year change for just a 50-degree temperature change. So if there's one thing I want you to remember from this talk, it's that when it comes to temperatures and volcanoes and understanding those timescales, temperature matters. Thank you.
Thanks. And again, that was Karalee Brugman. I believe I said her last name wrong accidentally. Next up, we have Andrew Lloyd looking at the full waveform adjoint seismic tomography of the Antarctic plate. You guys have a mouthful of words for me to say today.
Thank you. So my work on a full waveform tomography model for Antarctica was inspired in part by a need to better understand how the solid Earth interacts with the Antarctic ice sheet so that modelers can improve glacial isostatic adjustment models and ice sheet modelers can take into account the solid Earth effects correctly within their models so that we can better understand how the Antarctic ice sheet will behave in the future. For them to do that, they need constraints on the lithospheric thickness and variations in viscosity. And these rheological properties are important because they're going to determine the timescales at which the solid Earth responds to a change in ice mass loss. And we can estimate these parameters from our 3D structural seismic models. But for this problem, we need a model that spans a large area and has high resolution in the upper mantle and possibly even in the transition zone. So to do this, we use adjoint tomography. It's a newer waveform-based method that's highly computationally intensive. The model that I'll show a bit of today took about 3 million CPU hours to produce and spans the area shown there with the white dashed lines. We use 277 earthquakes and over 300 seismic stations in Antarctica, many of which were deployed over the last decade and a half. So we've done a lot of work there. We'll focus specifically at West Antarctica, and this is showing you two depth slices of the shear wave velocity structure that we get. Big feature that pops out are these slow velocities along the West Antarctic coast. And as you go to deeper depths, they move offshore beneath the Amundsen Sea and Bellinghausen Sea. Now, slow seismic velocities suggest warm mantle temperatures and lower viscosities in the mantle. So this suggests areas like Pine Island Glacier and Thwaites Glacier, where we have the most ice mass loss, is actually underlain by a low viscosity zone. And the solid Earth in this area is going to respond very rapidly to changes in ice mass loss. Now, Antarctica is quite heterogeneous, as we can see here through this cross-section. We have these slow velocities along the coast. As we move inland into the interior of West Antarctica, there are more average velocities and fast seismic velocities beneath the East Antarctic Shield. Differences in seismic velocities suggest strong differences in rheological properties. So different areas of Antarctica will respond at different times, on different timescales to changes in ice mass loss. If you're interested to hear more about the model that we've been working on, I have a talk tomorrow morning. So thank you.
Thank you, Andrew. And next we'll have Begum Topcuoglu. Tried. Stress management skills in the subsurface, H2 stress on the thermophilic heterotrophs and methanogens.
Hello everyone. I'm going to tell you about how high temperature living microbes deal with stress in the hot subsurface and how they cooperate to do this. Why do we care about cooperation in the hot subsurface? It's because there's a large prokaryotic biomass in Earth's crust that we know very little about, and estimated 35% of sediments are above 60 Celsius, so it's pretty hot. And we know that 1 gigaton of methane gets produced globally per year by cooperation among microbes, but we know very little about this is in the above the surface and normal temperatures. But if you go to hyperthermophilic, high temperatures, we know very little about the cooperation that happens and how much methane gets produced from that. So the kinds of microbes that cooperate with one another are hyperthermophilic heterotrophs. These are anaerobes. They grow optimally at 82 Celsius. They can use sugars and peptides, degrade a lot of those, and produce hydrogen. The most well-studied genera are Thermococcus and Pyrococcus. The other genera that we're interested in are Methanocalococcus. These are hyperthermophilic methanogens. They are also hyperthermophiles, growing at optimally at 82. And they are a one-trick pony. They can make energy and make a living from only one reaction, and that's reducing carbon dioxide with hydrogen all the way to methane. And I'm interested in this phenomena, hydrogen syntrophy-driven methanogenesis. The organics get degraded by the heterotrophs. They produce hydrogen. This hydrogen feeds the methanogens, and they make methane from it. If there is too much hydrogen in the environment, we found out that the heterotrophs are inhibited, so they will benefit from having a syntroph taking that hydrogen away. And for the methanogens, it's always good for a syntroph to produce hydrogen so that they can make a living. And I approached this to understand and model this behavior by field experiments, chemostat growth, kinetic measurements from those, high-throughput sequencing, and modeling of the cell's behavior. Thank you.
Thank you. And now we have Chao Gao on quantifying uncertainties of seismic Bayesian inversion application to the northern Great Plains.
Okay. So when an earthquake happens, seismometer will record the ground motion as a seismogram, and seismologists can then make measurements from that contains the information from the Earth's deep interior. And here I listed the observables that are often used to study the structure of the Earth. And in this study, we'll be using receiver functions and surface with dispersions. And here in these three panels, I show an example of these two data types in red color. And as you can see that they might not directly reveal the structure of the Earth, we can perform a seismic inversion to do so. So during the seismic inversion, can I play the movie? No, the movie. There's a movie. So during this one, left, bottom. No, this the one before.
Here, why don't you, Chao, just,
Yeah.
There it is. All right.
So during the inversion, we iteratively propose 1D velocity profile, and to predict what the data would look like, and which is showing in the black, and then we compare our model prediction to the observations to see how good is our model fitting the observations. And ultimately, we search for an ensemble solution that represents the model probability given the observation. And such inversion process are applied to 320 seismic stations from the transportable array in the northern Great Plains of the US, which covers a geologically diverse area. And on these slides, the three figures across the diagonal shows the average shear velocity from our inversion result at different depths. And at 2 kilometers, 2 areas stand out with low velocities used, which we interpret as the signature from the Williston Basin and the Denver Basin. And at the lower crust depths, we see the contrast between the cratonic areas and the surrounding areas, with the cratonic areas such as the Superior Craton and the Wyoming Craton being much faster in terms of seismic velocity. And if you go to upper mantle depths, we see this clear east-west dichotomy, which has also been seen in other studies. So since in our method we search for an ensemble solution, we're also able to quantify the uncertainties in our result. So here is a cross-section at the latitude of 46 degree, and below is the uncertainty from the inversion. And we can see that the bulk of the crust is constrained to plus minus 0.1 kilometers per second. And in our inversion, the number of model parameters is set as the unknown to invert for. This allows us to quantify quantities such as the number of the layers in the crust, which is often set as a fixed number in the seismic inversion. And thank you.
Thanks. And next we will be going with Chelsea Allison, a thermodynamic approach for modeling water carbon dioxide solubility in alkali-rich mafic magmas at mid-crustal pressures.
All right, thank you. So the goal of this research is to use thermodynamics to describe volatile solubility. And the primary, that didn't change.
It's the top
one. There we go. Okay. So the primary question that we want to answer is, how does the composition of a magma, specifically for magmas with low silica but high concentrations of alkali elements, sodium and potassium, how does that affect the amount of volatiles that are dissolved at certain temperatures and pressures? So solubility tells us about volatile exsolution, and exsolved volatiles form bubbles, and bubbles are one of the primary drivers of explosive volcanic eruptions. So this low silica, high alkali compositional range that we're focused on is found at volcanoes all over the world, from Arizona to Italy, even in Antarctica. And high concentrations of alkali elements have been found to increase CO2 solubility, meaning that magmas with high alkali concentrations can dissolve more CO2 than magmas with low alkali contents. And magmas can be stored in the middle of the crust, and so it's really important to understand volatile solubility in this pressure range so that we can properly interpret volcanic eruptions. And as you can see on this plot that I have up here of total alkali content and pressure, these are the existing experimental data, and what you can see is that the middle of the crust is not as well studied as the upper crust. So we conducted a new set of experiments to help fill in some of these gaps in the middle of the crust. So we studied 6 different compositions, but we don't only want to know about these 6 volcanoes. We want to understand solubility for all magmas in this compositional range. So we use our new experiments as well as some experiments from the literature, and we take a simple thermodynamic model, and then we define the input parameters for that model using a simple compositional relationship, and that's our general model. And what's really great about this general model is that we can then examine how different elements in a magma affect CO2 solubility. So what I have on this plot here is the CO2 solubility at 500 megapascals. So we have a starting composition shown by the star, and then we increase each element in the magma by a little amount and then recalculate the solubility using the model. And so what this shows is that for these types of magmas, sodium and calcium actually very strongly control CO2 solubility. So let me finish by quickly applying this to volcanic data from Stromboli volcano from a highly explosive eruption. So previous models calculated that the magma was stored at about 7 kilometers depth, but with our new model, we find that it's actually stored about 2 kilometers deeper at 9 kilometers. And so this shows how important volatile solubility is to interpreting volcanic eruptions. Thanks.
And next we have Chris Marsh, who is looking at simulating complex cold region process interactions using a multi-scale variable complexity hydrological model.
Which one controls it?
Near the bottom.
Excellent, thank you very much. So mountains in the world have been termed the water towers of humanity. They provide a critical source of water for downstream users, and this is really important for arid and semi-arid downstream locations. But in order to make good water management predictions, we need to be able to simulate and understand the snow processes that occur in the mountains. And this is a global phenomenon. In this picture here, the red areas are the locations which contribute substantially to downstream flows. And including all of these processes in the models can become very difficult, and under climate and other anthropogenic changes, some of the previous assumptions we use produce results that aren't quite correct, and it becomes more difficult to produce good water management decisions. This is especially true in the Rocky Mountains in Canada, where under climate change we may be seeing up to 60 fewer days with snow melt, or with snow cover, which can dramatically impact snow melt. So in order to better quantify anthropogenic changes in these regions and able to test our hypotheses to be able to improve process representations and to ultimately improve water management decisions, we really need improved modeling capacity going into the future. So we'll be able to integrate existing science, investigate all these multi-scale processes that we see, and then be able to take advantage of all of the new data that are coming out of the next generation satellite and remote sense platforms. So the Canadian Hydrological Model, CHM, is a model that I've developed as part of my PhD, and it's a distributed model tailored for cold regions. But one thing that it really does novel and new is it's able to scale from both the point to the plot, basin, regional, provincial, and ultimately continental scale. And it does so using an efficient novel terrain representation that allows us to have the detail where we need it and be able to use a more coarse representation where we don't. So this dramatically reduces the uncertainty, and it allows for more efficient computations, and so we can more readily look at our predictions. It's going to be towards a next generation forecast model, and if you want to see more of what we're doing with that, take a look at snowcast.ca, where it's producing forecasts of winter snow cover in the Rocky Mountains. So thank you very much.
And next we have Christian Kienholz, who's looking at accessing the inaccessible, making successful field observations at Tidewater Glacier termini.
Thank you. I'll talk about our research at LeConte Glacier, which is a tidewater glacier terminating in LeConte Bay, Alaska. Tidewater glaciers are controlled by processes that are inherently difficult to observe and understand. For example, submarine melting and calving, which happens right at the glacier face, shown here. To improve our understanding of tidewater glaciers, to be able to model them into the future, which is an important task in light of global climate change, we need more observation at the glacier-ocean boundary. This ocean boundary is actually a highly dynamic place where warm ocean water mixes with glacial runoff. As this unstable mix wells up along the glacier face as a turbulent plume, it melts the glacier, triggers calving, and ultimately drives larger-scale fjord circulation. Now, LeConte Bay provides an ideal natural laboratory to actually investigate these processes, especially because it is accessible year-round, which allows us to observe the seasonal variability in the processes of interest. As of this fall, we completed our 6th and final campaign, and I'm now touching on 3 selected field experiments. The goal of our first field experiment was to measure submarine melting directly. For that purpose, we deployed shipborne multibeam sonar, which reveals the submarine topography, including submerged glacier face. Repeat scans of the glacier face then yield submarine melting rates, of course, only after accounting for ice flow and calving, which we do through radar and photogrammetry surveys. Then a second experiment aimed at sampling the upwelling plume. For that purpose, we used drone boats that can go all the way to the glacier face safely. These boats, for the first time, provide a 3-dimensional picture of the plume through current, salinity, and temperature measurements. Then a third experiment aimed at quantifying the large-scale fjord circulation in LeConte Bay. For that purpose, we deployed time-lapse cameras, which covered the entire fjord at 2-minute intervals over 18 months. Iceberg tracking on the imagery reveals characteristic circulation patterns in the fjord, as shown here with the outgoing plume between 2 eddies. Currently, we are synthesizing the data from all our field experiments, and here at HU, we have 2 more presentations that present this data in more detail. Thank you.
And next, we have Danielle Blatter, quantifying uncertainty, or wait, we have a slight name change, Bayesian estimates of model parameter uncertainty.
Hello, everyone. I'm Daniel. And as a scientist, I use applied mathematics tools to image the electroresistivity of the subsurface. These tools are collectively called geophysical inversion, but that's just a fancy name for an attempt to get at the answer to a pretty broad and fundamental question. Let me explain it this way. Say I had a system I wish to better understand, like this coastal hydrologic system, where maybe pumping from groundwater for agricultural purposes has caused saltwater intrusion. Now, because freshwater is more electrically resistive than saltwater, if I knew the electrical resistivity of the subsurface, then I could be able to infer where the saltwater had intruded to. So the first thing I do is I create a model of the subsurface, in this case a 1D stack of layers, each of which has an unknown electrical resistivity, whose values I wish to know. Then I collect a field data set, in this case a transient airborne electromagnetic data set, that contains information about subsurface electrical resistivity. And then, third, what I need to do is come up with a function f, which takes as input my model parameters, and predicts the data I would measure if my model were an accurate representation of the subsurface. But what I really want is a function f inverse, which takes as input my data, which is what I actually know, and outputs my model parameters, which is what I don't know. The problem, though, is that f inverse doesn't exist, because there are many, many models that can satisfy my data and explain them equally well. And in standard inversion tools, pick just one of these many models, leaving me uncertain as to how much I can trust this model. But fortunately, there is a better way to go about it, namely Bayesian inversion methods, of which Markov chain Monte Carlo is a powerful example, attempt to sample from the full space of all the models that can satisfy the data. The conventional approach gives me just one model here, but the Bayesian approach samples fully from the space of all models and can give me an estimate of the range of model parameter values that are consistent with the data. And this is an example of Bayesian inversion from an airborne TEM data set collected over Antarctica. The x-axis is log 10 resistivity, the y-axis is depth, and warm colors indicate high probability density. So one way to read this plot is to take, look at a particular depth and just read across the plot. Here's the 5th percentile, the 95th percentile, and that dotted line is the only estimate you get from conventional methods, whereas Bayesian inversion gives you a full and rich estimate of statistical uncertainty. Thank you.
And next we have Danielle, Santiago, Ramos, looking at assessing the role of clay autogenesis in the seawater potassium cycle, a paired potassium and magnesium isotope study of deep soil pore fluids.
It's the bottom keyboard. Hi, everyone. I'm an undergrad at the University of Washington, and I'm really excited to talk to you about some research that I'm doing asking the question, does climate care about land? So land is really important in the climate. On the left, what we can see is a dark evergreen forest. And here, this is a really low albedo, and this is high absorption. On the right, we have a much lighter deciduous canopy, and this is a much higher albedo and absorbs less radiation. So if you're changing a forest from evergreen to deciduous, we would expect to see changes in absorption. And here, we're looking at the climate effect from these sorts of changes. So I have decreased the albedo everywhere, and what we can see, so that's corresponding to a darker vegetation, what we can see is temperature is increasing globally. But there might be more that is mattering besides albedo. There might be other things impacting the climate. And it turns out evapotranspiration is also really important. So plants have a latent heat flux that comes up, it cools the surface. But this cooling is actually putting a bunch of water vapor into the atmosphere. And water vapor is a greenhouse gas, which means that it traps heat, and it's warming the surface. So what we can see is that there are a lot of changes in vegetation in the Arctic. Here we can see the green is more Arctic greening, so almost everywhere in the Arctic there's a lot of greening. So now I have set up some model experiments to test these different contributions and look at how does albedo change and how does evapotranspiration change. So evergreen has dark surface, it's hard to evaporate. I prescribe these values into everywhere 60 north, above 60 north, and then I use this in an Earth system model coupled to an idealized land model. I also do an experiment that's easier to evaporate and an experiment with a lighter surface. So these 4 experiments then let me isolate albedo and evapotranspiration, and I can ask the question, what is the greatest feedback? So these experiments are currently being run, And when they're finished, we are going to be able to quantify the climate impacts from water vapor changes and albedo changes, which is going to improve our understanding of vegetation's role in climate change.
Next, we have Elizabeth Widener. Implementation of an acoustic-based methane flux estimation methodology in the Eastern Siberian Arctic Sea.
All right, thank you, Kelly. So last fall meeting, I introduced a methane flux estimation methodology using broadband split beam echo sounder data. And today I'm going to be talking about its implementation. So first off, why methane flux? So methane is a greenhouse gas, powerful greenhouse gas, whose atmospheric concentrations have increased over 150% since the Industrial Revolution. And in all ocean basins, marine seeps, like those that are seen in the image here, transport methane from the seafloor into the water column. And in the Eastern Siberian Arctic Ocean, which is this component of the Arctic Ocean, several decades worth of research have suggested that the shallow water column facilitates the transport of that methane into the atmosphere. But the question is, how much methane is there getting into the atmosphere? And that's really difficult to discern due to the broad spatial extent of this region and the heterogeneity of seep activity. So as part of the SWIRIS C3 expedition, we implemented our methodology in the Herald Canyon region. So we identified 89 individual seeps, and using our methodology, we processed them, which resulted in 150 individual bubbles that were sampled for bubble size and bubble rise velocity, both of which are important components of a flux calculation. So this equation gives flux. We have Q, which is flux, is a function of bubble size, the bubble size distribution at the seafloor, which is the rho of A term, and the rise velocity of the bubble, which is the V of A term. So on the left figure, we have the bubble size distribution in the water column. 90% of the data fall between 1 and 5 millimeters in radius. And if we look at the overall distribution of the data, it's best described as log normal. Both of these results are consistent with previous studies that use more traditional camera-based estimation methodologies. If we go to rise velocity, we can see that we have rise velocities varying between nearly standstill to almost 50 centimeters per second. And if we plot expected model rise velocities of clean and dirty bubbles, we can see that the majority of our data fit the sort of expected trend. Now, when we went to implement this methodology to calculate flux, or Q, what we found was that we didn't have enough individual data points to estimate the seafloor bubble size distribution. And so we weren't able to completely estimate flux. But what we did find was that we were able to very easily identify bubble radius and rise velocity from our data, and our uncertainty estimations allowed us to theoretically constrain flux as well as or better than traditional methodologies, meaning that we should be implementing this methodology when we can in future flux studies. Thank you.
And next we have Aaron McDuffie. When the sun's away, N2O5 comes out to play. An updated analysis of ambient N2O5 heterogeneous chemistry. It's the top.
Okay, great. Good afternoon. My name is Erin McDuffie. I'm a graduate student at CU Boulder, and today I'm going to introduce you to the atmospheric chemistry of N2O5 and highlight its importance to U.S. air quality during winter. So this first requires just a very basic understanding of its atmospheric chemical mechanism. As seen, N2O5 will form in any urban environment at night from the oxidation of NOx emission sources, from those such as cars and power plants. After formation, N2O5 can be destroyed at sunrise, forming NO2 and ozone, or it can react heterogeneously with aerosol to eventually form even more particulate matter. But it's really the ultimate fate of N2O5 that is important, because NO2, ozone, and particulate matter are all regulated pollutants that uniquely impact air quality. The fate of N2O5 is currently described using the N2O5 uptake coefficient, or gamma, which describes the reaction rate between N2O5 and aerosol. Gamma is highly variable, with small values largely leading to gas phase production at sunrise, and larger or more efficient uptake leading to more particulate matter. We also include uptake in current climate and chemistry models that are used to predict future climates. And our ability to predict its value during winter is currently limited by a lack of wintertime field studies. So to fill in this gap, our group participated in 2 recent aircraft campaigns where I combined these data with a chemical box model to derive uptake coefficients over the US East Coast in winter 2015 and this last winter over northern Utah. And uptake coefficients are very, very challenging to derive because they require many auxiliary observations, but the resulting distributions from these 2 campaigns have really allowed us to assess what factors control uptake, as well as its potential impact on air quality, which is largely dependent on whether gas phase or particle phase species are more likely to be formed. In fact, uptake was so large during our Utah study that our preliminary analyses are suggesting that the majority of haze formation in this region is from this nocturnal N2O5 chemistry. And this is contrary to previous predictions that haze formation was primarily a daytime process. So this new finding has very important implications for this region where 80% of the population lives and already experiences the worst air quality in the US during winter, and it will become even more important due to rapid population growth, making our understanding of N2O5 chemistry on air quality even more important in the future. Thank you.
And next we have Aaron Finch, who's looking at constraining the energetics of explosive lava-water interactions.
Thank you. So during volcanic eruptions, magma can interact explosively with water. This can be in the form of groundwater or surface water that's been melted from ice or snow. A good example recently is the Eyjafjallajökull eruption in Iceland in 2010. We call these eruptions phreatomagmatic eruptions, and this interaction with water can increase the intensity of these eruptions. The reason why they're so difficult to study is because not only is the external water expanding rapidly and fragmenting and dispersing magma, but the gas bubbles within the magma are also doing the same thing. So in order to try to constrain the energetics of this external water contribution, small-scale laboratory experiments have been performed. They found that explosion energy is largely made up of kinetic energy, which is proportional to the dispersal distance of the ejecta, in addition to fragmentation energy, which is proportional to the grain size and mass percent of ash size material of the ejecta. So we take the novel approach of studying explosive interactions between lava and water, because lava does not have the same kind of gas expansion within the molten melt as in magma during an eruption. So only external water is driving these explosions. As you can see at point 3, as explosion energy increases, the dispersal of ejecta also increases, producing larger cones. And the fragmentation also increases, producing finer grained beds. So we studied a wide range of deposits over 2 cones, a small cone and a large cone, relative to each other. And you can see in that graph that the mean grain size range that we found for these beds is quite large. And as mean grain size decreases, as beds become finer grained, the ash mass percent increases, which is something that we would expect. You can see this is much more the case for the large cone, which is built from more energetic explosions. So we studied this ejecta in a lot of detail, and now we can kind of go back to the computer and use these field constraints to start to constrain the energetics of these explosions as an important analog for phreatomagmatic eruptions. Thank you.
Next we have Eugenia Heung, ultra-high precision isotopes, the global budget, and paleoceanographic potential.
So isotopic variations of various Earth's surface materials like rocks, sediments, or waters can be used to trace and understand different geochemical, geophysical processes that are taking place or have taken place in the Earth's surface environment. So during my PhD work at the University of Southern California, I set out to put some of the first constraints on the isotopic composition of germanium, shorthanded as delta 74 GE, in various low temperature settings. Germanium is a trace element that is closely coupled to silicon chemically, and it has 5 stable isotopes that can fractionate during geochemical reactions. And the neat thing about germanium is that the crust is isotopically homogeneous, so there's very little variation among different silicate rocks in their delta 74 GE composition, and so we don't have to worry about source mixing and can use it as a process tracer. And so essentially what I found during my PhD are, number one, that rivers are generally isotopically heavy and quite variable relative to the silicate rocks. And that's a result of the precipitation of isotopically light secondary clays and soils during weathering. Number two, that seawater is also isotopically heavy and well mixed, and essentially represents a mixture of the two main sources of germanium into the ocean, which are rivers and hydrothermal fluids. Number three, that there's some isotopic fractionation during precipitation of autogenic clays and marine sediments, which is one of the two major sinks of germanium from the ocean, and so it can affect the seawater value. And number four, that there's no fractionation as far as we can tell during germanium uptake into biogenic silica of diatoms and burial of this biogenic silica in the marine sediments. And therefore, diatom paleorecords could be used to reconstruct germanium isotopic composition of the seawater in the past and put some of the constraints on these different processes like silicate weathering or hydrothermal activity or oceanic bioproductivity in the past. Thank you.
Thanks. And now we have, next we have Jennifer Walker, a robust definition of the South Asian monsoon onset and retreat.
The monsoon season in South Asia begins with a dramatic shift from dry spring conditions to a wet summer with intense rainfall and strong winds from the southwest. Then after several months of heavy rain, the monsoon tapers off in a more gradual retreat. Now, the timing of these transitions is crucial for managing water resources and agriculture, but it's actually quite difficult to define the monsoon onset and retreat in an objective and consistent way. Many different definitions have been proposed in the literature, but these mostly rely upon somewhat arbitrary thresholds in rainfall or winds, which are susceptible to false onsets triggered by transient weather systems and may no longer be applicable as the climate warms and the baseline climatology changes. In our study, we've introduced a robust new definition for monsoon onset and retreat, which does not rely on any thresholds. Instead, we use change point detection in the net precipitation, P minus E, which we calculate from the vertically integrated moisture flux convergence, averaged over a large-scale domain shown in the black rectangle. Using MERA-2 reanalysis data, we construct daily time series of P minus E over each year, as shown for an example year 2000. Then we compute the cumulative sum of this time series from January 1st, so that we're looking at not just a single point in time, such as this one, but the entire history up until that day of the year. Next, we find the day of the year, which minimizes the RMS error in a two-phase linear regression from days 1 to 250, as shown in the blue. This is our first change point, the monsoon onset. We apply the same method to the second half of the year to find the second change point, the monsoon retreat. Putting it all together, we find that the rainy season is well captured by our definition of onset and retreat, and pre-monsoon rainfall peaks, like this one, do not trigger false onsets. Applying this method to all our years of data, we find there's a range of 31 days between our earliest and latest monsoon onset, and our onset dates are well correlated with other published indices. Since our method does not use any thresholds, it's very robust and well suited for assessing variability and trends in monsoon timing over a wide range of climate scenarios. Thank you.
Next, we have Joseph O'Rourke, New Perspectives on the Accretion and Internal Evolution of Venus.
Good afternoon. Venus is arguably the most Earth-like planet in our solar system. It is just a little bit smaller and a little bit closer to the sun. But we don't know whether or not Venus hosted water oceans or even life for billions of years. And these uncertainties, including many other first-order aspects of Venus history, reflect a broad ignorance in our general knowledge of the evolution of rocky planets. So my recent work focuses on one way in which Venus is unique, that Venus is the only planet without any known evidence for internally generated magnetic field, either now or in the past. And we don't know whether or not rocks that record ancient magnetism are present on the surface of Venus because atmospheric interaction with the solar wind confounds observations that have been made from orbit. So my methods involve numerical simulations of the coupled evolution of the atmosphere, mantle, and core. Mantle melting releases greenhouse gases like water and carbon dioxide that vary the surface temperature over time. And the surface temperature determines whether the mantle convects in the mobile, stagnant, or episodic lid regime. And the heat flow from the bottom of the mantle sets the boundary condition for the core dynamics and thus controls any magnetic field. And I use a model for the core that I recently developed to model the history of Earth's dynamo. And I find that the thermal conductivity of core fluid is the crucial parameter in these simulations. If the lowest plausible values are correct, then a Venus with an Earth-like core would have a magnetic field today, as shown by the red line. In this case, the Venus must have completely solidified its core or preserved a primordial compositional stratification, both of which would indicate that Venus formed under relatively low temperature conditions without giant impacts. But if high values of thermal conductivity are correct, then Venus with an Earth-like core might not have a magnetic field today, but it could have had one in the past. So future missions to Venus should focus on making magnetometer measurements for the first time at low altitudes below the ionosphere. And if we detected any crustal remnant magnetism, that would be powerful evidence that Venus and Earth formed under similar conditions. And in general, we need to know more about Venus to complete our understanding of rocky planets in our solar system and beyond. Thank you.
So now we have Katherine Kumamoto. Size effects and olivine control strength in low temperature plasticity regime.
Is it going to be the top? All right. Hi, everyone. All right, I'm here to talk to you today about olivine plasticity. Now, olivine, do we have this green mineral on the left? This green mineral on the left makes up the majority of the upper mantle of the Earth. And as such, we often use the behavior of olivine as a proxy for the behavior of the entire upper mantle. Thank you. So in this study, we were interested in understanding the strongest part of tectonic plates, which are thought to be dominated by the behavior of olivine in low temperature plasticity. Now, several studies have looked at olivine in low temperature plasticity over the past 40 years or so, these gray curves here. And so the key thing to take away from this diagram, which has strength on the x-axis and depth into the Earth on the y-axis, is where these gray curves intersect with that black dashed line, as this should describe the strongest part of a tectonic plate. And as you can see, all of these gray curves intersect that line at a different point, indicating a lot of disagreement between different experiments. And all of these experiments are over-predicting tectonic strength relative to this blue line, which represents the strength of geodynamic models and geophysical observations. The question is, why all this disagreement? Our study revealed the presence of a phenomenon known as a size effect. Now, size effects can be summarized as smaller is stronger. In our study, which used a nano indentation experiments, we have an example indent up here in the top left and a map of the geometrically necessary defects around that indent here. We found that smaller indents yielded at higher stresses, or they were stronger than larger indents. And looking back at past experiments, these red dots here, we found a very similar pattern, that experiments on samples with smaller grain sizes yielded at higher stresses than experiments on samples with larger grain sizes. Now, the presence of this size effect explains all of the discrepancies that we saw between these different experiments, because there is this grain size effect. And that also explains why experiments overpredicted mantle strength relative to geodynamic models and geophysical observations, because the mantle is predicted to have a very large grain size. All right, this study was recently published in Science Advances, so if you would like to know more, you can go read the paper. Thanks.
Next, we have Katherine Goodrich, Twist and Shout Reconnection by Untwisting Tangled Magnetic Field Lines.
All right, thank you. So here I'm going to give you a twist on your preconceived notions of magnetic reconnection. So classically, the view of magnetic reconnection is opposite magnetic field lines merging together. There's a conversion between magnetic and particle energy, then the magnetic field lines split apart in a new topology. So the processes governing what this energy conversion isn't very well known, but a great way to observe these are in the Earth's magnetosphere, where reconnection is thought to occur but where the Earth's magnetic field in green meets the magnetic field that's output by the solar wind in yellow. So we think that reconnection is likely to occur at the day side and the night side, where the magnetic fields come back together in the Earth's magnetosphere. So that's where we sent the Magnetospheric Multiscale Mission, or MMS, which is a close proximity 4 spacecraft mission with very high resolution, time resolution instruments. And what we found is magnetic reconnection doesn't always occur cleanly. It doesn't always reconnect in one straight line and the magnetic fields separate evenly. It can be patchy. It can reconnect at multiple different points where the magnetic fields can become tangled, and the tangled magnetic field lines have to resolve themselves somehow. And the theory that we've put out is that a parallel electric field can work to untwist the tangled magnetic field lines. And sure enough, we see observations of twisted magnetic field lines and large amplitude parallel electric fields, both at the day side and the night side of the Earth's magnetosphere. And so in this case, we found that magnetic reconnection is confirmed at both of those places, but all that's really necessary are twisted magnetic field lines, which can happen anywhere in the Earth's magnetosphere. Thank you.
Next, we have Lucas Price work towards monitoring unstable glaciers with ambient seismic noise.
You'll be the top. Thank you. Yeah, thank you for this opportunity to present my work. I would also like to acknowledge that this work has been funded by the Swiss National Science Foundation. Unstable or avalanching glaciers are a big threat in alpine countries like Switzerland. And that's already the next slide, but that's fine. It's on autoplay. Okay. Yeah, it's a bit fast for me, so thank you. So if you see this unstable glacier that is frozen just next to the very famous Eiger North Face in Switzerland that all climbers will probably know, but an avalanche or an ice chunk that could break off there would cause an avalanche that could reach down to the train station, which would have devastating effects. And what we do is we put seismometers on these unstable glaciers in order to see what's going on inside before these glaciers break off. What we know from geodetic and GPS measurements is that these glaciers, these unstable glaciers, accelerate before they break off. And with the seismometers, we hope to see inside what's going on. And we observe two things. So this acceleration leads to induced fractures, which then are visible in a lower seismic velocity because there is more air that has a lower seismic velocity than the surrounding ice. So if you do these repeated measurements, or we use a technique like seismic interferometry, we do this virtually, we see that the seismic velocity is reduced before a breakoff. And secondly, we know, or we have observed, that the resonance frequency of these ice seracs is lowered as the crevasses get deeper before a breakoff happens. And our ultimate goal is to produce more headlines like this, where this summer, even the Washington Post acknowledged that we could evacuate the town before something happened. Thank you.
Now we have Malcolm Itter, estimation and application of ecological memory functions in time and space.
That's my last slide.
Let's cheat a little bit. Nope. Okay.
Is that my only slide? Really? I checked it yesterday. Really? Uh-oh. Well. Ooh. I can talk for 2 minutes about it.
Yeah, that'd be great. Go
No
for it.
slides.
No slides time.
All right. So here we go. I get 2.5 minutes. Yeah, all right. Well, I have no slides, so we're going to wing it. So basically, I was going to give you, or what I'll give you is a very brief and broad overview of the different spatial temporal factors that impact forest systems. And so, so what I was going to talk about was you have a variety of different factors that impact regional forest systems operating in a variety of spatial temporal scales. And so you can have regional species composition would be determined by climate on a centennial to millennial timescale. But that climate can also impact forest systems at much shorter timeframes as well through the occurrence of climate extremes such as drought events. You can have disturbance events that operate at a variety of spatial temporal scales. So you might have a wind throw event that knocks down individual trees within a forest stand. You can also have larger scale disturbance events such as a forest fire, which might reset forest successional pathways at a landscape scale and impact forest processes over the coming decades to centuries. And then within individual forest stands, we have a variety of forest demographic processes such as growth, regeneration, individual tree mortality that drive forest change over time. And so we can think about these different factors such as climate, abiotic disturbance, biotic disturbance, impacting forest systems. And these factors aren't independent of one another, rather they exhibit complex interactions. And there's various feedbacks between these factors and the forest ecosystems themselves. And so the key is that they all exhibit some form of spatial temporal dependence. And so we want to try to incorporate some of that spatial temporal dependence into our models of forest change. And so one way that we can do that is through this concept of ecological memory, which basically allows us to estimate over time the relative importance of past environmental conditions on current forest ecosystem function. And so we can actually estimate these ecological memory functions that allow us to estimate the cumulative effects of past environmental conditions on current function. And this gives us a lot better ability to understand and predict these complex forest processes. So if you're interested in learning more, you can go ahead and look at that website, and there'd be some visual cues and papers and so forth that would help you to understand what I'm talking about. But that's what I have.
So next we're looking at Margaret Zimmer. Spatio-temporal stream flow generation processes in a low-relief ephemeral to perennial drainage network.
Ephemeral, probably.
Yeah. All right, thank you very much. I want to first start by thanking my OSPA mentor, Gordon Grant. All right, today I will be talking about how streams form, where stream water comes from, and stream-groundwater interactions. All right, so here is a picture of a watershed with a river network. We know that groundwater enters river networks vertically from below, laterally from riparian zones, and longitudinally from upslope. And the importance of each of those different directions of flow paths matters in landscapes differently. And so there have been quite a few studies around the globe in various locations that have looked at the importance of those different directions of flow paths on where stream water comes from. And so these sites vary in soil depth and average topographic slope. But if you put the Duke Forest Research Watershed, which is where I do my hydrologic research, we see that historically many field sites across the globe have been biased toward steep regions with very shallow soil. And so there's a knowledge gap here of how do deep systems generate stream water. So to fill this knowledge gap, I monitored the spatial and temporal stream flow, groundwater, soil moisture, and precipitation at the Duke Forest across 2 years. For today's quick talk, I will be focusing on stream-groundwater interactions at one representative hill slope at this field site. Specifically, I will be showing you results, data from stream-groundwater head gradients. And so on the x-axis, we have time, and on the y-axis, we have head gradient, which is just the stream level divided by the groundwater level monitored in the hill slope. And so we have periods of the year where there is a positive head gradient that's color-coded in blue. And though a positive head gradient means that groundwater is entering vertically or laterally into the stream network. This occurs in winter conditions. We also have negative head gradients, which are color-coded in red, and those occur in summertime, and that's where we have a losing stream gradient. And these bidirectional flow paths have great implications for understanding how streams dry up in summer and how we recharge drinking supplies in our groundwater. And this leads me to a question that I will be addressing at my talk on Thursday about how all of these different flow path directions fit together and how they influence stream hydrobiogeochemistry. All right, thank you.
Next, we have Margaret Garcia. Conflicting epistemologies and inference in coupled human and natural systems.
Good afternoon. Today I'm going to talk about the philosophical underpinnings of coupled human and natural systems, or CHANS research, and the implications for modeling these systems. So, interdisciplinary research is often cited as a way to tackle domain-crossing challenges such as sustainability. But when we can bring methods and theories together from different fields, and this can be a really powerful approach. But when we do this, we combine areas of knowledge that make different underlying assumptions about the nature of the system and about how knowledge is created. So for example, aspects of CHANS systems can be considered mechanistic, while others can be considered adaptive or constructed, meaning that they are relative to the individual. And so what are the implications of bringing together this mix of different underlying assumptions when we want to evaluate models of these systems? So take, for example, this model that combines aspects of the hydrological, engineered, and social system of an urban water supply system that I presented last year. Sorry, I lost my train of thought. So there's, our intuition might be that subsystems, modeling subsystems of the engineered subsystems might have better model performance than, say, the social systems based on our underlying assumptions about how uncertain these systems are and how stable the processes are. And so we want to ask, what then can we learn, how can we then tackle model evaluation in this context? And so I want to present three open questions to tackle going forward. One is, can we quantify the uncertainty of CHANS models? How do we select among competing CHANS models? And how do we compare models across systems? And three quick ideas of how to tackle this. One is a pragmatic approach, where we judge models based on their utility. The second is a structured pluralistic approach, where we logically construct our evaluative criteria from the underlying assumptions. And the last is a information-based approach, where we judge models based on their ability to utilize available data. Thank you very much, and look forward to continuing the conversation.
And next we have Maya Buchanan. Household adaptive behavior in response to coastal flood risk and external stressors.
Hi, everybody. Thanks for sticking around. I think I'm one of the last. So today I'm going to talk to you also about the science policy interface a bit. And so what we know is that in the coastal area, 40% of the population is exposed to coastal risk from climate change. And that research, including mine from last year, focuses on how does sea level rise going to affect coastal hazards, how does this change people living in these areas and the exposure and the risks that they face just from the physical component. But people need to make decisions about how they're going to deal with this physical side, and that area is much rarely studied, sometimes AGU, sometimes not. But this adaptation will likely depend very much on the cooperation initiative of people, whether or not governments do anything. So whether or not they build some kind of physical barrier, like a storm surge barrier, or help increase wetlands, which some of you might study more in depth. And households are motivated by many different factors, and this area has actually been pretty well studied for different aspects of climate change, like agriculture and how farmers are adapting. But less so with sea level rise. And some of these that we focused on in our study have to do with this limitation of worry that people can handle and have on their minds, and also how influenced we are by what our peers do and other actors. So we did a study last year in Jamaica Bay in New York City, and it was to try and build an understanding of how households are adapting and how this can inform real-time government decisions about whether or not people might want to build a really expensive storm surge barrier or further develop wetlands. So building off of the old literature on socioeconomic factors and what might influence people, we also wanted to be very cognizant of the fact that there are few examples, we have few observations to work with in terms of how people are actually adapting in real time. And also a lot of these hazards to sea level rise and flooding are only beginning to manifest, and we expect nonlinear essentially changes over the next century, right? So our opportunity to deal with this was to pose scenario questions. It's called discrete choice experiments coming from economics, and we very systematically vary the conditions to elicit preferences that people have. And what we're trying to do is systematically understand which adaptation people may or may not take, not only with respect to sea level rise, but these other external stressors that people have to deal with all the time. And so the key findings that we found, to wrap up, is that homeowners who have already taken a very, very small and probably not very effective action, like storing up on batteries or water, were much less likely to take a larger scale adaptation like buying flood insurance or relocating, and that homeowners are many times more likely to relocate if their peers do, and 3 times as likely to relocate if there's nuisance flooding, which is understudied compared to extremes like Katrina that happened here. And also to finish up here, that renters are a lot less cognizant of these risks and taking less actions. Thank you.
Next we have Michael Afanasiev, expanding the frontiers of waveform imaging with, I'm going to go for SALVIS.
So what does medical imaging, non-destructive testing, and geophysical exploration have in common? Well, they all kind of rely on this ability to see inside some sort of hidden medium, or to basically create an image of an area that our eyes can't access. Now, the way we do this is by studying the vibrations of tiny mechanical waves, which kind of travel through some medium of interest, which carry information about that medium to the surface to some receivers somewhere. And while the character of those waves, the way they're set in motion, might vary dramatically, once they actually are in motion, the algorithms used to take the information out of them and create a 3D model of that object are more or less the same between all these disciplines. And it's this similarity which has driven collaborative and productive research across these domains for about the last half century. In the geophysical imaging community, something changed about 20 years ago. We realized that we were actually throwing away most of our data. And in fact, we were reducing the complexity of the seismic wave field to just a measure of the first arrival times, basically like one time sample at the beginning of these waves. The solution here was full waveform inversion, which was a new imaging technique which actually took the full complexity of the wave field into account and which used it to create a much higher resolution image of the target body. So over the last few years, myself and some other colleagues at ETH in Zurich have developed a new software package called SALVIS, which aims to basically take this imaging technique out of geophysics and apply it to a wider range of applications. We're currently working with non-destructive testing, where we're using SALVIS to basically image very small flaws and features inside solid mechanical objects, specifically in the areas of corrosion monitoring in pipelines and also structural health monitoring in bridges. Basically, wherever you find that there's a kind of a volumetric and diffuse heterogeneity that can't be imaged through classical ultrasound methods. We're also working with some colleagues in medical imaging, where SALVIS is being used to drive research into new forms of early breast cancer detection. And of course, our kind of bread and butter is global seismology, where we're using SALVIS to kind of investigate the effects that the crust might have on waveforms, which are investigated by the Mars InSight lander landing next year. So that's it. If you have more questions, you can check out our website or the research group at ETH. Thanks.
And next we have Pauline Lumiere, 2D potential theory using complex algebra, new perspectives for the interpretation of the marine magnetic anomaly.
Just a minute. The topic of my presentation is new development in theoretical in complex algebra on the marine magnetic anomaly. So the study of marine magnetic anomaly is important because we can estimate the age of the oceanic crust or the spreading rate of the ridge. But in my cases, I'm interested by the estimation of the apparent inclination of the magnetization, because when the crust cold under the crust temperature, the current temperature, we can estimate the paleolatitude of the crust. For example, here we have a model for anomaly 19 and 22. If we modified the apparent inclination of the magnetization, we have the variation of the shape of the anomaly. Here we have 5 per 5. But if we transform the real data profile in the complex domain, we obtain a complex representation in the complex plane. We have 5 curves. All the curves have the same shape, but we have a rotation in the complex plane. So we can permit to quantitative approach. Here it's a little example in the North Atlantic. We have aeromagnetic data in this area, and we are extract 30 profile here in the middle. In the right, we have a complex representation. We have all profile overlapping, and we can make automatic approach to estimate many parameters like phase, for example, in this application. Thank you.
All right, next we have Richard Vashula, Evidence of Ice Age Humans in Beringia. New insights on the peopling of the Americas. You're the bottom one.
Okay. Thank you for having me. So the motivating question of my research is, when did Homo sapiens arrive in the Americas? While it might seem like a really simple question, it's actually one of the greatest remaining uncertainties in our understanding of our species' history. So Homo sapiens developed about 200,000 years ago in East Africa and then relatively quickly proliferated throughout Eurasia. However, for nearly 30 years, it's been commonly accepted that humans didn't make it to the Americas until about 15,000 years before present. And that's largely based off of the earliest archaeological evidence of humans in Alaska at 15,000 years. And it's also corroborated by paleogeography as well as paleoclimate, which would suggest that this region would have been too cold and inhospitable for humans. However, several years ago, genetic evidence was found that would suggest that a population of Proto-Americans actually lived in Beringia for as long as 15,000 years prior to this 15,000 years before present arrival date. And so with that, we've been forced to reconsider this timeline. And so the way in which I've been testing this is by looking at 2 lake sediment records from north-central Beringia, and by measuring 3 proxies preserved in the sediment record. And so we can use the sediment record as an archive of paleo-environmental information. And so firstly, I've been looking at fire history signals in the form of charcoal, which are just particles, and then PAHs, which are biomarkers, both of which are produced during the incomplete combustion of biomass. And so because we're in a high latitude region with relatively limited natural ignition, we can use fire as a relative proxy of human presence in this region. Additionally, I've been looking at fecal sterol assemblages preserved in the sediment record. And so as you can see here, fecal sterols can be used to fingerprint the feces of different animals. And so by measuring the fecal sterol assemblages preserved in the sediment record, we can get an idea of whether or not there was human presence. And in particular, copper stanol is produced in the gut via the hydrogenation of cholesterol in human feces. And so just to briefly flash you with some results, what I've shown here then is just PAHs and charcoal data exhibiting really clear increased burning during the glacial period, contemporaneous with sporadic but consistent fecal contamination of the sediment record. And so in this way, we have new evidence that forces us to reconsider our understanding of the timeline of peopling to the Americas. Thank you.
And next we have Ray-Ju Wong. 2016 to 2017 update of hydrologic fracturing-induced earthquakes near Fox Creek, Alberta.
Good afternoon. I would like to talk about earthquakes triggered by industrial activities, commonly known as induced earthquakes. One of these activities is called multi-stage hydraulic fracturing, as illustrated by the figure on the left hand. So a well is drilled horizontally along the shale layer for about 1 kilometer, and large amount of fluids are injected to enhance oil and gas production. One of the famous, in some cases, more than one well could be drilled from a shared well pad. One of the famous shale gas formation is Burnett in Western Canada, as shaded in the figure on the left side. Within this region, Fox Creek used to be a seismically quiet zone with less than 1 magnitude 2 event per year. Since 2013, the seismicity has increased substantially. So only in the past 2 years, hundreds of magnitude 2 to 4 earthquakes happen in this place, as indicated by those red dots. So this figure shows how we link a seismic swarm to industry activities or a suspected well using the temporal relationship. In this figure, the x-axis is date in January for 2016, and the y-axis on the left side is injection pressure, as indicated by those blue bars. There are 26 stages of multi-stage hydraulic fracturing stimulations in total, and no event occurred before the injection. About 2/3 of the earthquakes happened during the injection, and the magnitude 4.8 events happened in the last stage. Our statistical analysis indicate that these two are associated with each other at a confidence level higher than 99%. So the next step is to understand how this happened. This is again a figure of the Fox Creek area, and the red dots are the earthquakes. The red beach balls here, the focal magnitudes may tell the answer. So we loosely refer those focal magnitudes as beach balls, and the red ones are events in the past 2 years. The two perpendicular lines on these beach balls indicate two possible fault orientations, either the north-south or the east-west orientation. Researchers now believe that fluid migration is a key reason for the reactivation of unmapped faults, and our analysis of the aftershock distribution indicate that north-south is the true fault orientation. This is also consistent with the regional geological observations of the flower shape of faults, as shown on the right side. Taken together, we conclude that hydraulic fracturing caused the slip of those flower type of faults in this region and caused the earthquakes. Thank you.
All right, and next we have Sahani Pathiraja, Model Uncertainty Quantification. Great, and next we have Sarah Fletcher, Water Supply Infrastructure Planning Under Multiple Uncertainties, a Differentiated Approach.
So water supply infrastructure planning is a critical process to make sure that we can provide high quality, reliable supply of water for decades in the future. And this process is impacted by several uncertainties: supply variability in the environment, demand growth, climate change. And these uncertainties have different characteristics. Some of them arise from natural stochastic variation in the environment, like rainfall and runoff, while others arise from a lack of information. And some of them are more or less difficult to quantify probabilistically. We can use different planning paradigms to manage these uncertainties. If we wanted to use robustness, we'd like to develop a strategy that, since we don't know what's going to happen in the future, can perform well in as many different future scenarios as possible. That's in contrast to adaptability or flexibility, which is the idea that since we don't know what's going to happen, we might like to be able to react and adapt as uncertainties unfold over time. These elements inform each other, and we might want to use different planning paradigms in order to manage different types of uncertainty. In particular, I look at the potential for adaptability or flexibility to manage uncertainties that arise from a lack of information, but can be reduced as more information is collected over time. Flexibility can take many different forms in our water policy, the operations of our infrastructure, the planning processes, or in the physical design of the infrastructure so that it can be more easily retrofitted over time. I develop a planning framework that allows us to assess the potential for flexibility to mitigate risk. First, I classify different types of uncertainties, paying attention to which ones can be reduced over time as more information is collected. Then I develop different planning or infrastructure alternatives, some of which are flexible and some of which are not. And they're evaluated using a system model and then a decision model. And that decision model uses a stochastic multi-stage optimization approach, which allows us to explicitly model the potential to collect new observations over time, update our predictions probabilistically, and then adapt and react using flexible options. I apply this to a case from Melbourne, Australia, where the government built a $3.5 billion desalination plant that lay idle for the next 5 years. It was totally unused, unneeded afterwards. And I demonstrate that using a flexible infrastructure approach where capacity is added modularly can save an expected $1 billion over its lifetime with similar reliability. So to conclude, different uncertainties have different impacts on water supply systems, and flexibility is expensive, but it's often valuable when opportunities exist for learning over time. So planners should proactively assess whether upfront investments in flexibility are useful in managing uncertainty in the future.
All right, next we have Sebastian De Pasquale. Van Allen probes investigation of the plasmasphere response to geomagnetic activity.
All right, so this week you'll likely hear, see, or talk about research enabled by space technologies. Unlike our predictive capability of understanding weather on Earth and its impact on many human activities, we are still at the stage of monitoring what I'll call space weather and its damaging effects on satellites today. Like terrestrial weather, space weather results from the influence of the sun on Earth. Solar radiation produces charged particles in Earth's ionosphere that can escape gravitational attraction, only to be trapped by the magnetic field around Earth in a donut region of plasma known as the plasmasphere in space. The sun also has an outward stream of charged particles from its atmosphere, but these charged particles form a plasma known as the solar wind that drags the solar magnetic field across the planets. The relative orientation of this magnetic field with the orientation of Earth's magnetic field interacts and exchanges energy and charged particles, creating the phenomena of space weather. If we take a horizontal cut across that diagram on the top and look from the top down over the pole at the plasmasphere region, showing here the density content of this plasmasphere drawn to scale with respect to Earth's axis, radius, out to the location of GPS satellites in color on a log scale, we see that the influence of the solar wind imparts an electric field across the plasmasphere that has the effect of drawing plasma away from Earth, eroding the plasmasphere towards the sun. As that influence diminishes, the force of the magnetic field takes over and co-rotates this plasma around Earth, and over time, the outflow from the ionosphere refills the plasma to its pre-undisturbed state. Using observations shown here to the same scale as the model previously from the Van Allen probe's mission, I've demonstrated that the simple empirical model is capable of matching estimates of refilling from more complex simulations, suggesting that we can couple the simple simulation with larger framework to gain a global picture of space weather to protect our local space assets. Thank you.
Next, we have Jesse Halm, the influence of critical zone structure on runoff paths, seasonal water storage, and ecosystem composition.
Near the top keyboard.
Okay, thank you. So if you live in a Mediterranean climate, you probably take it for granted that you can cool off in a stream or under the shade of a tree in the summer. But you may ask yourself, where is the water in that stream or in that tree coming from? After all, in these seasonally dry climates, it doesn't rain for 6 months straight in the summer. Of course, the water is coming from below ground, where it's stored in soil and in weathered rock. Recently, scientists have defined this near surface layer of the Earth as the critical zone, and it extends from the top of the fresh bedrock, meters below the ground surface, upwards to the top of the vegetation canopy. With colleagues at the Eel River Critical Zone in Northern California, I study how the critical zone soaks up water like a sponge in the winter and slowly releases that water to plants and to streams in the summer. We do this by drilling deep boreholes and looking at the weathering profile, monitoring groundwater and unsaturated zone moisture dynamics, gauging stream runoff, and quantifying the sap flow in trees. One of our most important findings is that the entire thickness of the critical zone, that is, the depth of that thick weathered rock layer, is a key and crucially important variable for understanding surface ecosystems. And that's because trees in this climate are not just using water from the near surface shallow soils, but in fact from the entire thickness of the weathered rock profile. To demonstrate this point, I'd like to introduce you to two landscapes in Northern California, an evergreen forest and a deciduous oak savanna, which inhabit two of the belts of the Franciscan complex. At the evergreen forest site in the summer, trees tap water that's seasonally replenished at up to 30 feet below the ground surface in the fractures of mudstone. In the oak savanna site, the fresh bedrock is actually only 6 feet from the ground surface, and most of the rains, when they fall in the winter, rapidly run off the landscape as overland flow into the streams. I should mention that the climate is basically identical in both of these places, and it's pretty wet. Last year in the winter, we got more than 10 feet of rain at these sites. Another consequence of the limited storage at the oak savanna site is that there's insufficient drainage from the critical zone to support base flow in the summer. And as a result, the streams run dry fairly early in the dry season. Our findings have important implications for understanding the biogeography of tree species, and they're also important for understanding how rock type influences the habitat of endangered salmon species in our study area. Thank you.
Next, we have Xiaomeng Jin, using satellite data to guide mission control strategies for surface ozone pollution.
And you'll be the top keyboard.
Hello, I'm Xiaomeng Jin from Columbia University. So my research interests the chemistry of air pollution, especially surface ozone pollution. So today I will share a story about how we use observations from space to inform emission control strategies for surface ozone pollution. So surface ozone is an air pollutant, which is bad for human health and vegetation. The making surface ozone requires two ingredients. One is NOx, and the other is VOCs. So NOx are oxides of nitrogen, which is emitted from fossil fuel combustion. VOCs are volatile organic compounds, which can be emitted from both fossil fuel combustion and also the biogenic activities from trees. So the ozone production is somehow dependent on the relative abundance of NOx versus VOCs. But it's actually very hard to measure them, especially at a large scale. Satellite instruments cannot measure them either, but they can measure them. They are proxies, nitrogen dioxide and formaldehyde. So we use that observed ratio of the formaldehyde to nitrogen dioxide as an indicator of the relative abundance of NOx versus VOCs. High ratio often means the ozone production is limited by NOx, where the NOx emission reduction is more effective than VOC emission reduction to control ozone pollution. Low ratio, on the other hand, often means the ozone production is limited by VOCs, where the VOC emission reduction is effective, while the NOx emission reduction is counter-effective. So a major goal of our research is to identify the threshold values that can separate the NOx limited versus the VOC limited chemistry, and then apply this method to long-term satellite observations. So here I'm showing you the time series of the ratio of the formaldehyde to nitrogen dioxide in Los Angeles from 1997 to 2016. And the pink band here shows the regime threshold value, below which is VOC limited and above which is NOx limited. And the bottom panel shows the ozone production as a function of NOx. So here you can see that in early period, before 2007, the ozone production in Los Angeles was VOC limited throughout the year. That is, during this period, NOx emission reduction could actually lead to the increase of ozone. However, just because of the continued effort to control NOx emissions in Los Angeles, the Los Angeles has finally made the transition to NOx limited regime. So for now, if you ask what is the most effective emission control strategy for Los Angeles, the answer would be to control NOx. So that's a very simple yet important message that we can get from satellite data. Thank you very much.
Thanks. And now we have Yiling Wang, to trust or not to trust, what drives public trust in science and social media engagement.
Good afternoon. My name is Yiling Huang. I'm a PhD candidate at the Australian Centre for Astrobiology at UNSW, and my research is the impact of social media engagement on public trust in science. We have all heard these stories before, the anti-vaxxers, the climate change skeptics, the evolution deniers. Here's an uncomfortable truth. Science today suffers from a legitimacy problem. Now, why is that? To borrow a phrase from Billy Joel, it's a matter of trust. The erosion of public confidence in science is a big problem today. Thanks to their built-in architecture for participation, social media have been hailed as the shiny new tool in the scientist's toolbox to engage with the public and restore public trust. However, there has been very little research on the impact of social media science communication on public attitude towards science, and my research aims to fill this gap. My background is in engineering and computer science, so I use machine learning and big data analysis methods to approach my research questions. In the first part of my research, I built a predictive model using supervised learning to investigate the factors that make a science message engaging. And my results showed that visual elements, anger, authenticity, a tentative tone, and hashtags are the unique features of highly engaging space science-related social media messages. The second part of my research focused on examining the impact of social media engagement with scientists on public trust in science. And I found that social media engagement with scientists is associated with higher levels of trust in science. And the most effective predictors for trust-inspiring science-related social media messages are similarity, the presence of URL, and again, authenticity. It is noteworthy that authenticity is the only feature that inspires both engagement and trust. This shows that social media science communication is not as straightforward as we engage, therefore they trust, and scientists should be aware of the nuances that characterize communications on virtual platforms. The world increasingly needs scientists to also be advocates for science, so don't be afraid to be yourself. Be authentic, be honest, be open, be weird if you have to. Be human. It's important and it works. Thank you.
I'd like to give a big round of applause to all the speakers, all the mentors who helped them out, and all their folks back at their home institutions that allowed them to come here. Thank you very much. And next, I know I promised you a little bit of time for questions, but we're going to torture you first. If we could ask every one of the speakers and the mentors in the room, both the ones that helped out with the presentation as well as their scientific advisors who are still around, to come up to the front of the room. We're going to go up in front of the screen that says "Be Human" and take a quick picture. Yeah, you didn't know this was coming. I'm sorry about that, but picture time, and then we can chat and have questions over the coffee break.